So the next type of optimization problems are ones where we are talking about an area of a shape that's actually inscribed in another shape. And so what's happening in this case, let's just kind of cut to the chase here. We got a right triangle that has a vertex on the graph of y equals 16 minus x squared, another at the origin, and another on a positive x-axis. All right, so that sounds like a lot. It is a lot of language, but let's just essentially break it down. So first of all, why don't we go ahead and just graph y equals 16 minus x squared. So if I did a sketch of that, right, this sketch is basically a parabola, right, that goes all the way up to 16 and then it's opening down. As a matter of fact, I think it's crossing the x-axis at -4 and 4 respectively if we look at intercepts real quick. So here is the sketch of this function, y equals 16 minus x squared. And then putting the right triangle together, here's what they're telling us. They're telling us that one vertex is actually on the graph itself. So maybe it's that point right there. They're saying another one is at the origin, so perhaps it's that point right there. And then they're saying another is on the positive x-axis. So we're not going to consider that part of the graph. We're going to be on the positive x-axis right there. And so there in blue is my right triangle with all the vertices on the right spot. So one vertex is on the graph of y equal 16 minus x squared, one's at the origin, and one's on the positive x-axis. And so you can imagine, right, let me go ahead and change colors. If my point was over here, then my right triangle is going to change a little bit, right? Or if the point's up here, then my right triangle is going to change yet again. So the area is dependent on where am I at, right? What's my x value down here? Because that'll basically change my location on the graph, which basically changes this vertex on the graph and changes this location on the x-axis, and it basically changes the shape of the right triangle. And what we're going to basically eventually do is try to find what's the largest triangle we can fit in there. So that is what's happening here. This is where we're inscribing a right triangle within another graphical shape. All right, and so we begin this journey then to find the area as a function of x. Let's just figure out what the area of a rectangle is. And we know that the area is 1/2 times the base times the height, right? That's a classic rectangle formula, whether it's right or not a right triangle. And when we look at this, it looks like the base is equal to what x is, and the height is basically the y value, right, given for that for the right triangle that's graphed. So my a is 1/2 times x times y. And so here is the function that we need to minimize or maximize, and the constraint, the y, is constrained by the equation 16 minus x squared. So if I change x, you notice that the y value changes along the edge of the circle, or excuse me, along the edge of this parabola by that equation. So what comes next? We're going to take that constraint and replace that y. So a is equal to 1/2 x and then 16 minus x cubed. And there you have it. So if we kind of work that out, I think this becomes, let me write it down here, a of x looks like it's 1/2 16 times x, right? And then minus 1/2, oops, that's a square, right? 1/2 x cubed. So our area is -1/2 x cubed, and I think that's plus 8x. So you give me x now, any value, then I'll tell you what the area of the rectangle, the right triangle is with regard to that. And I think I did my math all right. Right? So 1/2 of 16 is 8x, and then 1/2 x cubed. And again, this is definitely not a quadratic, so we're going to be reaching for our calculators to find that largest value here in a moment. But right now, why don't we go ahead and just use our function. The first thing they're asking us to do is find the area of the triangle when x is 3. So I'll just basically plug 3 into there. So we got -1/2, 3 cubed, plus 8 times 3. And I believe this will be a -27/2 plus 24. Finding a common denominator, this is a -27/2, and that would be 48/2. And so it looks like we're going to get something over 2, 48, 18, 3, 15/2. So about 7.5. So when x is equal to 3, right, perhaps it's this, here's 4, so maybe 3 is right about in there, right? The area of that right triangle is 7.5, or 15/2. All right, so that's how we basically do that. Another question that is important here is what's the implied domain for this function? Because this guy here has, its domain is from -infinity to infinity. So this has a very strong domain, but we're kind of restricting ourselves to what's happening here. One of our vertices is at the origin, one of them is on the positive x-axis, so we're not going to consider this stuff over here. And then we don't want to have over here, my areas would be negative, and that doesn't make any sense. So this problem only makes sense if our x values are between 0 and 4. And I guess interval notation, right, that would be 0 to 4. So that would be the implied domain. This function is only a good function. Even though everything else is defined for everything, this function only works when we keep our x values between 0 and 4. And so that'll impact our graph here in a moment. So when we do go to do the next question, which is to ask what is the largest triangle that we can fit in there, right, we're going to go to our graphing calculator, and probably the first thing I want to do before, well, let's go ahead and enter the function. I like to use parentheses, so we got -1 divided by 2, and then that's basically x to the 3rd power, right? And then we're going to add 8x to that. And then what I'm also going to do when I go to my window, since we have a restricted domain, I don't need from -10 to 10. So how about we go from just from -2 up to 6. Oops, -2 to 6. Because we really are interested in just from 0 to 4, right? What's the graph look like over that implied domain? And let's just leave y min and y max the way it is right now. We can play around with that later. So when I go graph this, right, I do see that I have somewhat of a graph. There does seem to be a high point up here somewhere. So that basically means we need to change our y max to get that value. So let's go to window. And how about we go out to, just go out to 20, see what we get there. And so there's basically the shape of the graph. We can clearly see a high point. So again, we're only interested in the graph from 0 to 4. And this is basically giving us the area, right, of my right triangle underneath that curve there, that inscribed part. And there definitely is a location, there is an x value that gives us a max. So when we go find that, so second calculate, we'll look for a maximum value. I got to make sure my cursor is just to the left of that maximum value. I got to make sure my cursor is just to the right of that maximum value. And then I got to give myself a guess. And so homework wise, right, you're going to show me a quick sketch, right? We're from -2 to 6 and -10 to 20. And the sketch pretty much looks like this. And so that high point is occurring at x equals to 2.309, how about we say 4. And then we know the y value is 12.3168. Of course, that y value is our area. So when we come in somewhere along this x-axis, right around 2.3, how about we say that's it? This right triangle that I have colored in blue, that's the largest right triangle that we can create. It occurs at x equals to 2.309, and its area will be 12.316, which is definitely higher than the 7.5 we calculated earlier. And by the way, just to verify that we're right there, if we go second calculate a value, I think I said when x is 3, yeah, when I let x equal to 3, right, we get 10.5. So I think I was a little off there. I know why. 48 take away 27 is 21. You guys are probably screaming at me, right? Unfortunately, if we were in a class, you guys could have told me that right away. So 21 over 2, right, turns into 10.5. So now my picture matches my math, especially after I did that subtraction right? Yes, 48, take away 27. Yeah, it's 21, not 15. I don't know what I was thinking. Alrighty, so there you have it. So again, the dynamics are going to be pretty much the same. We're going to try to draw our shape. I think the homework does a pretty good job. They actually show you a picture of the shape, but if there's not, you can piece it together. Get a good picture, figure out what your area is for the shape, plug in our x and y coordinates, because that's usually what's going to happen, and then you use your constraint equation to replace the y, and you now have a function of x. You can answer all your questions, and you can do all your maximum minimums based off of that rhythm. So we'll do it another time for another shape in a video coming soon.